Greetings! In this lecture, I will provide an overview of wastewater treatment. We will look at energy consumption in the collection and treatment process, and then in a later video, we'll look at least 2 case studies involving wastewater treatment plants. We can think of the typical wastewater treatment plant as having 3 distinct parts. The first is raw sewage pumping. Typically, the sewage flows through the collection system by gravity. However, there are often locations in the collection system where the wastewater must be pumped to a point of higher elevation. In such situations, a pumping or lift station is used. A pumping station is typically designed to handle wastewater that is fed from an underground gravity pipeline and stored in an underground pit or wet well. The wet well is equipped with electrical instrumentation to detect the level of water present as shown here by the level float switches. When the water rises to a predetermined level, the pumping station commences operation. A pump starts to lift wastewater upwards through a pressurized pipe system that discharges the wastewater into a gravity manhole or inspection chamber. Here, the cycle starts again until the wastewater reaches its destination, usually a wastewater treatment plant. The wastewater then flows through the treatment plant. Ideally, the wastewater would flow by gravity through the plant. However, that is often not the case and pumping is needed. In activated sludge systems, the aeration blowers are the largest energy users. The last part of the plant is sludge handling. Sludge must be pumped from the bottom of sedimentation tanks to the ground surface for treatment. We typically divide wastewater treatment into 4 steps: pre-treatment, primary treatment, secondary treatment, and tertiary or advanced treatment. Pre-treatment removes the larger material: sticks, kids' toys flushed down the toilet, wipes that shouldn't have been disposed of in the toilet, grit, sand, and other large material. It also includes flow equalization, which is used to equalize both the flow rate and strength of the wastewater. Primary treatment uses gravity settling to remove the settleable material, about 60% of suspended solids and about 30% of biochemical oxygen demand. Secondary treatment includes biological treatment, which is necessary to oxidize soluble BOD. The wastewater effluent is then disinfected. If chlorine is used as a disinfectant, the wastewater effluent is dechlorinated before it is discharged into the receiving body of water. If the effluent needs additional treatment, then it is processed through tertiary treatment before discharge. This can include filtration to remove particles that did not settle in a secondary clarifier, or adsorption for the removal of specific organic chemicals and/or heavy metals. Phosphorus can be removed through precipitation or additional biological treatment. And finally, nitrogen, it can be removed also by additional biological treatment. As previously mentioned, the sludge or solid materials produced during sedimentation must be treated before disposal. We don't have time here to go into all of the processes used for sludge treatment, but these are a significant part of a treatment process and often significant energy consumers. The 2 basic types of biological processes are suspended growth and fixed growth. With suspended growth, the microorganisms are dispersed throughout the suspension of wastewater. With fixed growth, the microorganisms are attached to a solid support. The water flows past the attached microorganisms in the same way that water in a river flows past the algae growing on rocks alongside the side of the river. Activated sludge is one of the most common suspended growth biological processes. The suspension is aerated to ensure sufficient oxygen is present to promote the degradation of BOD. Oxidation ditches are similar, although they have sequential aerobic and anaerobic zones. Aeration is achieved either by mechanical aerators shown in the top photo or rotating brushes shown in the lower photo. Lagoons are low-technology pond-like bodies of water. Mechanical aeration may be used in aerobic lagoons to ensure sufficient oxygen levels in the water. With trickling filters, the water is distributed over a bed of rocks or plastic media to which the microorganisms are attached. Typically, a rotating nozzle distributor is used to spray wastewater over the surface of the bed. Biotowers are similar to trickling filters. Lastly, rotating biological contactors are similar to trickling filters in that the microorganisms are attached to a solid surface, in this case, rotating corrugated discs. The wastewater is aerated when it is in contact with the atmosphere. Roughly 90% of the energy consumed at a treatment plant is from the wastewater treatment process, with aeration being the single largest energy consumer. Blowers, like pumps, are large users of energy. UV disinfection is becoming more common at water and wastewater treatment plants. This is also a high energy consuming process. In all cases, the energy use for the processes on site is much greater than that for the buildings, which comprise about 9% of the energy utilized. Wastewater treatment plants present many opportunities for energy recovery. An energy balance for a wastewater treatment plant is shown in this figure. The influent to these facilities contains chemical, thermal, and hydraulic energy. Chemical energy is stored in the various organic materials in the wastewater. Thermal energy is contained in the wastewater. Hydraulic energy is related to the flow of water through the plant. Typically, purchased energy in the form of electricity and natural gas is used to treat wastewater. Wastewater treatment generates biosolids and biogas, which contain chemical energy. The wastewater effluent has recoverable heat and hydraulic energy. Before beginning a process energy audit for a wastewater treatment plant, it's important to request from the client energy bills and process data for the last 3 years. Process data should be available if the system is using a SCADA. Additionally, it's important to obtain site drawings, flow diagrams, results from any previous energy audits, agreements with the electricity and gas companies, climate data, and pump and blower curves. In planning for the energy audit, you should determine if the client has an energy team, an energy leader, and who is the decision makers within the organization. Implementing any future changes will require their support. Before scheduling the first site visit, discuss with the client what they hope to achieve through the energy audit, the time frame, expectations, the driving factors of why they are completing an energy audit, and any site-specific safety and access issues. Lastly, review the drawings to ascertain what equipment is located at the plant and generate a list of equipment that will be evaluated during the visit. Make sure to ask lots of questions during the site visit. Common questions may include, are buildings or processes on the site sub-metered? How many electrical feeders are there? What is the wastewater utility's relationship with the electric utility? Does the wastewater utility have any ongoing capital projects? What are the future process challenges for the wastewater utility? Does the wastewater utility have a choice of electricity and gas suppliers? Are there city or state mandates for renewable energy? And what is the makeup of the wastewater customers who are part of the system? The measurements taken during a site visit will vary. As previously noted, energy use for the wastewater processes is higher than for building loads. However, it's still necessary to record building information. Much of the process data may be available from the treatment system through the SCADA, mentioned previously, that's Supervisory Control and Data Acquisition System. The SCADA system should be recording flows, pressures, and the runtime for major equipment. Be sure to obtain as much of this data as possible for future analysis. The plant laboratory will record data for wastewater quality. During the energy audit, obtain the energy consumed by the pumps and blowers. These include the dosing pumps for chemicals added to the primary clarifier and to the disinfection basin. It also includes both wastewater and sludge pumps. Finally, it will be critical to monitor the energy consumed by the blowers providing oxygen to the aeration basins. As previously mentioned, pumps are large energy consumers for wastewater utilities and often provide room for improvement. Make sure to also record the pump operating points, flow ranges, turn down range of the variable flow drives, wet well levels, and the maximum and minimum wet well set point possible. Check the actual pump speed and flow versus the pump curve. During the energy audit, obtain the operating speed of any rotating equipment. These include rapid mix basin, for instance, chemical addition in the primary clarifier, sludge and scum handling in the clarifiers, oxidation ditches, rotating biological contactors, and wastewater distribution spray nozzles on trickling filters. Now, it should be noted you won't find all of those in one wastewater treatment plant. For instance, you'll find either an oxidation ditch or a rotating biological contactor or trickling filters. Be sure to record the temperature of the process areas. Temperatures that are too hot or too cold may be a reason for poorly operating equipment. With most wastewater treatment systems, it is critical to monitor the dissolved oxygen levels in the aeration basins. For the buildings, be sure to collect the number of rooms, square footage of each room within the building, number of light fixtures and types, and details of the HVAC system. Be sure to record the temperature of all spaces and obtain the temperature set points for the buildings during summer and winter. Also be sure to obtain the startup sequence for major pumps if that information is not available from the plant's SCADA system. Some facilities may have an electrical monitoring and control system. Recording the startup sequence provides important data to understand startup loads that have a large impact on electricity demand charges. If the wastewater treatment plant has a filtration system, then be sure to obtain information on the backwash pumps for the filters. As previously mentioned, before the site visit review, you should review the as-built facility drawings to determine what equipment is at the plant and generate a list of items to be tested. Construct a spreadsheet to track all of the data you wish to collect. Pumping contributes to the energy profile for water treatment plants. There are many different types of pumps, and a separate course would be needed to cover all aspects of pump selection. However, during an energy audit, checking the pump sizing will be useful. Pumps should be operating at their best efficiency point for maximum efficiency. It is assumed that the reader is familiar with how to read a pump curve and how to use pump affinity laws. Aeration is used during secondary and tertiary wastewater treatment processes to remove BOD and nutrients. There are many types of aeration systems, such as diffused air, jet, or surface aerators. Diffused air aeration systems are very common due to their process efficiency, but are typically very energy intensive. Selecting the appropriate aeration type and sizing, the associated equipment to facilitate aeration is beyond the scope of this lecture. Many aeration systems use blowers. Checking the blower horsepower will be useful during an energy audit of a wastewater treatment plant. During the energy audit, you should look for some of the common methods of saving energy. Often these changes can be implemented without additional capital investment. Possible energy-saving tips for wastewater treatment plants include ensuring pumps operate at the best efficiency point, changing pump wet well set points, identifying areas where peak demand can be trimmed or shifted, shifting peak energy loads to off-peak hours, staggering or spreading out equipment and motor startups, and developing operational strategies to minimize pumping or other high-power demand system operation during periods of peak electrical demand or peak electricity consumption. Some energy-saving methods, such as those shown here, require further engineering analysis. These include developing a calibrated treatment plant process model, modifying control strategies to monitor energy performance, installing premium efficiency motors and variable frequency drives, reducing the energy required for aeration by using fine bubble diffusers, or installing dissolved oxygen probes to allow operators or an automated control system to adjust blower systems in real time. Additional energy-saving methods that also require further engineering analysis include implementing dose pacing instead of flow pacing for UV disinfection, purchasing smaller, more efficient equipment, generating power on site and using this power source during periods of peak power demand, installing a heat and power system or a gas-driven generator that uses the biogas generated from wastewater treatment, and installing solar panels or wind turbines to offset purchased power. I hope that this presentation has provided you with a brief overview of wastewater treatment and where energy is consumed during wastewater treatment. In a subsequent lecture, we'll look at several case studies where energy audits were conducted at wastewater treatment plants. Thank you and have a wonderful day.